We've looked at the derivative of a function of x. So if you have a function like y is equal to f of x, e.g., well, f of x. So f of x means a function of x. For example, y equals 3x squared. I've shown you how to determine the first derivative. So dy dx. In this case, dy dx is 6x. Now what we're going to do now is understand what this derivative means. This derivative is actually linked to the gradient of a point on a curve or a point on a straight line. And I'm going to demonstrate that relationship. Consider the function y is equal to x squared. This function can be plotted if I obtain a table of values. So I get some x values and find the corresponding y values. When x is 0, y is x squared, which is 0 squared, which is 0. When x is 1, y is 1 squared, which is 1. When x is 2, y is 2 squared, which is 4. When x is 3, y is 3 squared, which is 9, and so on. So a graph can be plotted. So I'll sketch the graph of y equals x squared. Graph of y equals x squared looks like this. I can also extend this region in this direction, but I just want to focus on this region, so I'm just going to drop this left hand part. So this is a portion of the graph y equals x squared. So this is the graph y equals x squared. So you can take this as the positive y-axis and this region as the positive x-axis. And on this graph there will be points. So I'm going to call this point A, point B, call it C. Each of these points have coordinates. So point A I'm going to call x1, y1. Point B I'll call x2, y2. Point C I'll call x3, y3. So what I'm going to do now is draw a line from point A to B. From point A to B, I'm going to draw a line. And from the algebra course, you know that the gradient of a straight line is given by the following formula. M is equal to y2 minus y1 divided by x2 minus x1. So you have a straight line and you have 2 points, where one point is a point A, x1, y1, and another point is point B, x2, y2. The gradient of that line is given by this equation. It has been discussed in the algebra course. So this is the line AB, and the gradient of the line AB is given by this formula. So I'm going to do something different now and relabel the coordinates. So the coordinates of point A I'm going to define as x and y. Coordinates of point B I'm going to define as x plus delta x, and the y coordinate is going to be y plus delta y. So the coordinates of point B are x plus delta x for the x coordinate and y plus delta y for the y coordinate. What does this mean? This simply means that I'm moving along this curve, and as I move from point A, which has an x coordinate of x and a y coordinate of y, I move to a point B, and as I move to the point B, the x coordinate increased by an amount equal to delta x. So I move from here to here, so the x coordinate of point B is x plus delta x. This interval here, as I move from A to B, the x coordinate changes from x to x plus dx, so the change is delta x. As I move from A to B, the y coordinate, so the new y coordinate is y plus delta y. So as I move from y to y plus delta y, the change in the y coordinate is delta y. I'll just circle these. So that's if I move from point A to B. So I'm just going to draw a line joining A to B. Imagine I move from point A to B along the straight line. The gradient of the line is given by the change in y divided by the change in x. So the gradient of line AB, so I'll write m line AB, where m refers to the gradient, is given by y plus delta y minus y. So this is changing y. So this is essentially y2 and this is y1. So I'll just make it clear. This is y2 and y here is y1. This is x2, so this is x1, and this is y1. As used in the formula, m is equal to y2 minus y1 divided by x2 minus x1 for a gradient. So y2 is y plus delta y, y1 is y, and x2 in this case is x plus delta x, and x1 is x. As you can see, x1 is x, and this gives y plus delta y minus y divided by x plus delta x minus x, and that's equal to, well, y plus delta y minus y, same thing as y minus y plus delta y divided by x minus x plus delta x. So I just grouped like terms. Y minus y is 0, x minus x is 0. So essentially what we have here is that the gradient of the line AB is equal to delta y divided by delta x. So the change in y divided by the change in x. Now, just starting from this expression, I can make some changes, or just from this expression. So either this or this. Let's start with this. Some changes can be made. Now, remember we have the graph of y equals x squared. And we have 2 points, point A and point B, and their coordinates have been given. The coordinates of point A are as follows: x and y. Coordinates of point B are as follows: x plus delta x and y plus delta y. Now, instead of writing y plus delta y, I can do something. Now, because all points that lie on this curve satisfy the equation of the curve, if I just focus on point B, the x coordinate of point B is x plus delta x. That means the y coordinate of point B, because it satisfies this equation, is equal to x squared. So the x coordinate all squared. So point B has the following coordinates: x plus delta x for the x coordinate, and x plus delta x all squared for the y coordinates. From expansion, the expansion procedure in the algebra course, you know that x plus delta x all squared is the same thing as x plus delta x times x plus delta x, which is the same thing as x into x plus delta x. So review the expansion course if you have to, plus delta x into x plus delta x. And this gives x times x, which is x squared, plus x times delta x, which is x delta x, plus delta x times x, which is x delta x, well, plus delta x times delta x, which is delta x, all squared. So I can simplify this to give x squared plus x delta x plus x delta x, the same thing as 2x delta x. You can think of x delta x as a variable like y or something. You know, y plus y is same thing as 2y. P plus p, same thing as 2p. pq, which is a variable, plus pq, is same thing as 2pq. So x delta x plus x delta x is 2x delta x plus delta x all squared. Therefore, this is what we have. Point A has the coordinates x, and instead of y, I'm going to write x squared, because remember, y is equal to x squared. That's the function we are focusing on. So if the x coordinate of a point is x, the y coordinate is going to be the x coordinate squared. In this case, that's x squared. Point B has the coordinates x plus delta x and a y coordinate of this. So we have a simple case. We have 2 points. This is x1, this is y1. So the first x coordinate, well, the x coordinate of the first point is the y coordinate of the second point. This is the x coordinate of the second point and the y coordinate of the second point. So back to that line AB, the gradient of that line, as you know, is, the gradient of line AB is y2 minus y1 divided by x2 minus x1, which in this case is equal to, what's y2? This whole expression here, so x squared plus 2x dx plus delta x squared minus y1, which is x squared, all divided by x2, which is x plus delta x, minus x1, which is x. So x squared cancels x squared here, x cancels x here, which leaves 2x delta x plus delta x squared, all divided by delta x. So the gradient of the line AB is equal to this. As I showed you earlier, I said gradient of the line is delta y divided by delta x. So delta y dx, that's how you read it or pronounce the name of the expression. So that means that delta y delta x is equal to 2x delta x plus delta x squared divided by delta x. So going back to the original graph, imagine that this point B, this same point B, was really close to point A, so somewhere here, and it had the same coordinates, because all these coordinates are telling you is that I have a point A and I have an x coordinate of x. The point B is another point where the x coordinate is x plus delta x, so just a slight increase in the x coordinate to move to the point B, and then the y coordinate just increases by a small increase, which is delta y. So imagine point B was here, so I'll just put a prime there. Imagine point B was there. The line joining A and B will be this line, and this line is essentially a tangent to the point A, and I'll just demonstrate that if you permit me to just draw another graph here. We have we have this curve, and I'm marking out this point as point A. Well, that's not clear. Marking out this point as point A, and this point right next to point A as point B. A line joining these 2 points is as good as a tangent to point A. That means that the gradient of the line joining AB in this case is the same thing as the gradient, or is essentially the same thing as the gradient of the tangent to point A. And if you remember or recall from the algebra course, if you want to determine the gradient at a point on a curve, you need to draw a tangent to that point and find the gradient of the tangent using this formula. This expression here, delta y delta x, that was obtained earlier, was obtained as follows: by finding the gradient of a line joining 2 points A and B. As you can see here, this was the first attempt, but here is what we have here. So the gradient of line AB, y2 minus y1 divided by x minus x1, a formula you're familiar with, and then I just replaced y2 and y1 with the actual values, and we got this expression here. And delta x just represented the change in the x coordinate. So in the graph here, started at point A, the x coordinate is x, and I moved to a point B with it. So the x coordinate is just x plus the change in x coordinate. And what I did subsequently was to move point B closer to this point A. So if you just ignore this, the coordinates of this point B is also x plus delta x. But if I keep moving B closer and closer to point A, eventually point B will be right next to A, or almost coincident with point A. So the change in the x coordinates will still be the x, but this change will be small. Essentially what is happening is, as B is moving closer and closer to A, dx, this change in x, is decreasing in value. Initially this dx was this big, so let's say that's a change in 2 units. Then it moved to this point here, let's say that's 0.5 units, and then ultimately it's getting close to A up until the point where this change in x is maybe 0.0000, so something really small, so essentially 0. And that's what I illustrated here. This is the case where point B coincides with A, so the change in x is really small, essentially 0. And for that situation, delta y delta x, which is the gradient of the line joining A and B, is the gradient of the tangent to A, which means it gives you the gradient of the curve at point A. And to do that, I have to say the gradient of the tangent at point A is given by dy dx, which is equal to this delta y, delta x. This is the notation as the limiting value of this as delta x tends to 0, which means that in this expression, which I'll simplify shortly, this expression is what you can do is divide, dx here 1, dx here 1, and then dx here 1, dx here, 1. What I'll do is I'll write it out. So this expression here is the same thing as 2x delta x over delta x plus delta x squared divided by delta x. So delta x here 1, delta x here 1, which gives 2x plus delta x here 1, and then in this is delta x. So we have 2x plus delta x. So what's the limiting value of, so this is delta y, delta x. So what's the limiting value of delta y, delta x, which is this, as delta x tends to 0? Well, that is simply obtained by replacing delta x with 0. So you get 2x plus 0, which is 2x. So dy dx is equal to 2x. So for the function y is equal to x squared, we deduce that delta y, delta x is equal to 2x plus delta x, and then the first derivative of the function dy dx, which is defined as the limiting value of this delta y, delta x as delta x tends to 0, is equal to this as delta x tends to 0, so we put the limiting value delta x is equal to 0, 2x plus 0, which is 2x. So what we just obtained is the following: dy dx, the derivative of the function y equals x squared, is 2x. I just showed you how to obtain that. I told you for a function in form y equals ax to the n, dy dx, the first derivative, is equal to an x to the n minus 1. So our function in this case is y equals x squared. So the same thing as y equals 1 times x squared. So a is 1, n is 2. So delta y, well, dy dx is equal to 2 times 1, 2, x into 2 minus 1, which is this, which is equal to 2x to the 1, which is equal to 2x. So which is the same thing as this. So this technique essentially gives you the result that was obtained by the long derivation I just showed. But the key thing I need to emphasize, and the main aim of demonstrating this, is as follows. The function y equals x squared was sketched, well, just a portion of it was sketched anyway. This positive x-axis, positive y-axis, and the sketch looks something like this. And there's a point A with coordinates x, y, and there's a point B with coordinates x plus delta x, and a y coordinate of y plus delta y, but I broke it down even further. Now, if you draw a line from A to B, the gradient of that line was obtained as, well, delta y, delta x, as I showed you earlier, and we ultimately obtained this 2x plus delta x. This was the gradient of the line. Now, if this point B, same point B, was moved here, and it had the same coordinates, it will have the same coordinates because what I'm just saying I'm just ignoring. Let's imagine that this point never existed, and this is actually where I put point B. So this x coordinate just says, look, the x coordinate here is x, the x coordinate of this point here is just this x plus, so an increase in x to give x plus dx. Ditto for the y coordinate. The y coordinate of this point is y, the y coordinate of this point here is just this y coordinate plus an increase in the y coordinate, which is delta y. So the y coordinate here is y plus delta y. So a line from A to B here will also have a gradient given by this expression. So what I said was, at some point, if you keep moving point B closer to point A, you get to a situation where point B coincides with point A. And a line joining, this is how to see, a line joining point A to B is essentially a tangent to this curve of y equals x squared at point A. And as you know from the algebra course, to determine the gradient of a curve at a certain point, you need to draw a tangent to that point and determine the gradient of that tangent. And that's what we've done here, because essentially this expression is the gradient of a line joining A and B. But in this case, this final case, point B coincides with point A, and the gradient of the line joining, well, let's say point B is very, very close to A, and the gradient of the line joining A to B is also given by this expression. But in the case where B coincides with A, so delta x is 0, what does that mean? Well, look at this. This is delta x in the second case. Delta x in the first case is as follows. This is original x, and this is the delta x. In the final case, delta x is very small. So delta x, this value here, is getting smaller and smaller. At some point it will tend to 0. In that case, when delta x is 0, what we have is dy dx, and dy dx is equal to the limiting value of delta y delta x as delta x tends to 0. So in the limiting case, I'm going to replace delta x with 0 in this expression, and that gives 2x plus 0, which is 2x. So we've essentially derived the gradient, or the first derivative of the function at any point. So I'll just rewrite this expression. It's the same thing as dy dx is equal to 2x, and this just means that the gradient at any point on this curve is equal to 2x. You wanted to determine the gradient at a point on the curve. What you normally do is draw a tangent to that point and then determine the gradient of that tangent. You know, a tangent is a line, so you can determine the gradient of a line. But because we can differentiate, all we have to do is say, okay, well, our function is of this form, so dy dx is equal to an x to the n minus 1, and this expression tells you the gradient at any point on the curve. All you just need to know is the point, the x coordinate of the point. So for this expression here, well, the function y equals x squared, the gradient function is dy dx, which is 2x. So it tells you that if you want to determine the gradient at any point on the curve, you just need the x coordinate of that point, and you need to multiply that x coordinate by 2. So for the curve, so for this, our same curve, y equals x squared. What's the y-axis? Now I'm going to give you some specific points. I'll call this point A with the coordinates. Let's call it A. So y equals x squared. Let's say this is the point 1, 1. So this is not drawn to scale. 1, 1. It's another point B. Point 3, 9. It lies on this graph of y equals x squared. If you wanted to determine the gradient at point A, you would have to draw a tangent to point A and then determine the gradient of that tangent. If you want to determine the gradient of point B, or the gradient of the curve at point B, you have to draw a tangent to point B. So you have to draw a tangent line and then determine the gradient of that tangent line. But because you can differentiate, you know that for the function y equals x squared, the gradient at any point, the gradient function is given by dy dx, which is equal to 2x. So if you want to determine the gradient at point A, instead of drawing a tangent and determining the gradient of that tangent, you just need to know that the x coordinate of point A is 1. So the gradient of the curve at point A, which is at the point where x is equal to 1, is given by 2 times 1, which is 2. The gradient of the point at point B is the point where x is 3, is given by 2 times 3, which is 6. So this procedure saves you from having to draw a tangent line and then determine the gradient of that tangent line. So you don't need to worry about the derivation of that expression, delta y, delta x. You just need to understand what I'm saying. The gradient function, dy dx, is essentially a tool for determining the gradient at any point on any graph. all you just need, well, in this case anyway, since dy dx is 2x, the gradient function is 2x, all you just need is the x coordinate of the point you're interested in, and you can determine the gradient at that point. So here's a summary of all you've just seen. In fact, if you just remember what I just said now in this short space of time, you don't even need to remember anything I said previously. So I'll just start from a straight line. From the algebra course, if you have a straight line with 2 points, so this is a point A with coordinates x1 and y1, and a point B with coordinates x2 and y2, the gradient of this line, m, is equal to y2 minus y1 divided by x2 minus x1. So that's the starting point, gradient of straight line. Next thing I want to move on to is the gradient of a curve. So any kind of curve. So imagine I have a graph and you just have a curve, right? So a quadratic curve, for instance, so something that looks like this. From the algebra course, you know or you remember that the gradient changes with points on the curve. So the gradient at each point, well, the gradient varies with the points on the curve. Unlike a straight line where the gradient at every point is constant, on a curve the gradient at every point on a curve is not constant. And you know that to determine the gradient at any point, so I'll just pick out this point here, point A, and I'll pick out this point B. If you wanted to determine the gradient at these points, you have to draw tangents to these points. So to determine the gradient at point A, you have to draw a tangent to point A. So a line that just touches this curve at just point A, and you need to determine the gradient of this straight line using this formula to determine the gradient of the curve at point A. Similarly, for this point B, to determine the gradient at point B, you have to draw a tangent to point B and then determine the gradient of this tangent, and that gives you the gradient of the curve at point B. We've covered this in the algebra course. Now, what differentiation does for you is as follows. For a curve especially, I mean for any function, but it's essentially beneficial for a curve. So you have a function, so y equals fx, so let's say you have y equals 3x squared, which will look something like, it will look like this. Now if you wanted to determine the gradient at this point, I'll call point P with coordinates 1, 3. From the algebra course, from what you learned, you want to determine the gradient at this point P, you have to draw a tangent to point P and determine the gradient of that tangent. Here's what differentiation does. In order to determine the gradient at point P, all you have to do is find the derivative of the function. So y equals 3x squared. What's the derivative? dy dx, which is equal to 2 times 3, 6, x to the power of 2 minus 1. So dy dx is 6x. So what this does is it gives you a gradient function. It tells you the gradient, or it gives you a tool to determine the gradient at any point on the curve, and you don't have to draw tangents. So for instance, for this point P, if you want to determine the gradient at point P, all you have to do is say, well, the x, or note that the x coordinate is 1. So to determine the gradient at point P, all you need to do is find dy dx when x is 1, because on this curve of y equals 3x squared, point P is the point where x is 1. So the gradient at point P is 6 times the x coordinate at point P, which is 6 times 1. So gradient is 6. So what you just realize now is I just determined the gradient at point P, and I did not draw a tangent, and I did not use this formula to determine the gradient of the tangent line. That's the key thing. If you remember everything I just said in the last minute or so, so just this last section of this video, then you've learned what you need to know. You don't need to worry about the original derivation and all that. The key thing here is to know that if you want to determine the gradient at a point on a curve, just write down the function. So in this case, y equals 3x squared. Determine the derivative, and then note down the coordinate of the point you're interested in and substitute the relevant coordinate into the derivative, and then you find your gradient. So in this case, dy dx is 6x. You want to determine the gradient at point P, where point P is the point on the curve where x is 1. All you have to do is replace x with 1 in the gradient function, because the gradient function here, dy dx, tells you that the gradient at any point is 6 times the x coordinate of that point. This x here refers to the x coordinate of the point you're interested in. And that's all.